This is part 8 of a series on Word2Vec. In this video, we'll implement a SkipGram model with negative sampling. In the last video, we looked at how to generate a training dataset for a negative sampling model and looked at how to train the model. In this video, we'll implement the model in Keras. First, load the preprocessed Gutenberg corpus. These are the vocabularies we generated and saved in this video. This time, we additionally use a frequency dictionary for each word. The vocabularies are as follows, and the word frequency dictionary is as follows. These are unique words present in the corpus, and these numbers are the frequency of occurrence of each word. If we convert each word in this dictionary to its corresponding index, it would be as follows. The second sentence in this corpus is as follows, and the corresponding sequence is as follows. These numbers are the indexes of each word in this sentence. NVocab is the vocabulary size, and NMB is the size of the word embedding vector, which is set to 16. The K value for negative sampling is set to 2. Next, we generate positive samples. We use 5 grams to generate the positive samples. In this sequence, C is the center word, i.e. the target word, and the rest are surrounding words, i.e. context words. We generate the positive pairs as follows, and assign label 1 to each pair. This indicates that each pair is a positive pair. The positive pairs generated from this sequence are as follows. In this 5-gram sequence, the number 453 is the target word index, and these numbers are the context word indices. This is the array xpos. Next, we generate negative samples. To perform negative sampling, we randomly sample words from the corpus according to the probability distribution we looked at in the last video. UOW represents the frequency of word W, and Z is the normalization constant. High-frequency words are selected more often, and low-frequency words are selected less often. Since we set the K value to 2, words twice the number of positive samples are sampled. The number of negative words sampled for each positive pair is typically 5 to 20 for smaller datasets, and 2 to 5 for larger datasets. Although we are using a small dataset, we set the value to 2 to simplify the model. Create an array xneg by repeating each element of the array xpos k times. The first column of this array contains the target words. Insert the negative word sampled above into the second column, and fill the third column with label 0. This indicates that each pair is a negative pair. Since this word was chosen randomly, these two words have no relation to each other. If the words in the first and second columns are the same, they are removed. merge the positive and negative samples into one array, and shuffle the pairs. This is the array xtrain, which looks like this. This array contains about 8 million pairs. The first column contains the target words. The second column contains the context words. And the third column contains the labels. Next, we create a SkipGram model with negative sampling. The structure of the model is as follows, and its implementation in Keras is as follows. We've already covered this structure in detail in the previous video, so I won't go into detail here. Create the model and compile it. Fit the model to the training data. Input the target words into the first input layer and the context words into the second input layer. And then we output the labels to the output layer. The batch size is set to 10,000 and the epoch is set to 1,000. Next, we plot the loss history to see how our model learnt and reduced loss over time. The results are as follows. You can see that the loss decreases like this during training. Next, we get the word embedding vectors contained in the shared embedding layer after training the model. Using this, we can obtain the embedding vector for each word. For example, the embedding vector for the word sun is as follows. Finally, let's see a list of words that are most similar to a given word. We write a function that finds the top n words in the word embedding space that are closest to the embedding vector of a given word. Let's use this function to find the 10 most similar words to the word sun. The results are as follows. The embedding vector for the word sun is similar to the embedding vectors for moon, star, etc. And the embedding vector for the word father is similar to the embedding vectors for brother, wife, etc. We can see that the embedding vectors of semantically similar words are similar to each other. In this chapter, we looked at the SIBO model and the SkipGram model through 8 videos. In the next chapter, we'll look at fast text word embeddings.